And my talk will be not very usual today because actually what I have been working on is ADS-CMT holography, which in full means anti-de Sitter condensed matter theory holography, is not a part of curriculum of conventional condensed matter physicists. Therefore, I decided not to speak at all about my own results in this field, but instead I'll try to provide a pedagogical introduction in this area, and then maybe I'll outline what can be done with ADS-CMT approach within this ERC synergy initiative regarding out of equilibrium processes. So motivation to apply ADS-CMT is very simple. So the main inspiration for our activity here is X-ray core spectroscopy. I think I don't need to tell you what it is. You probably know it much better than me. And the point of X-ray is that it provides a very deep ultraviolet probe of the material. And it allows to obtain electronic structure with high accuracy, and it is very sensitive to interfaces, surface effects, defects. So as an experimental probe, it is very nice. But when we think about it from theoretical point of view, we can consider two different regimes. In one regime, when field strength is not very high, we can consider X-rays to be just a probe. So we shine on our material with some hard photons. We read out what we collected. On the other side, we reconstruct spectrum, and in this way we can obtain symmetries of energy gap, dispersion relations. We can visualize real space charge and spin textures, but that's in the probe limit. However, if we proceed to higher field strengths, so from, let's say, synchrotron to X-FED, we have to deal with very strong reaction of these X-rays onto our materials. And instead of a probe, we have to deal with a perturbation. So we change our state significantly, and we can ask what kind of dynamics we can observe after this perturbation. So it becomes not a probe, but rather a local quench. So this quench can induce some new, unusual, large-scale emergent phenomenology in the material, and it would be interesting to describe it mathematically. So if the perturbation is not strong enough, and if the material is weakly correlated, there are conventional approaches to this problem. So the main one is so-called Mahan-Nazir de Dominicis theory, which I'm not going to speak about. I'm not a proper person to do it. But basically the idea is that you consider your material, then you suddenly change local potential on site by creating a hole on some core level of an atom. And then you can write down some self-consistent equations connecting your Green functions in unperturbed and perturbed material and describe time dynamics after a quench. But it works only for weakly coupled systems. Now, what if we deal with strong correlations? And here our proposal is to apply certain methods that came from string theory to study real-time dynamics of such systems. And now I need to change my topic completely and start speaking about quantum gravity. So let me start from the very beginning. What the holographic principle is. I think the proper moment when it first originated and when we should start speaking about it is when Jacob Bekenstein suggested that black holes are in fact thermodynamic objects and they have entropy. And he has shown that in order to obey laws of thermodynamics, entropy of a black hole must be proportional to its area. But now, if you think about it, we'll run in a kind of contradiction because, okay, area of black hole is proportional to its entropy. Entropy is related to the number of degrees of freedom, which is in turn proportional normally to the volume of your system. So area should be proportional to volume. Sounds strange. And the resolution of this contradiction was proposed by Thovt and Susskind in the early 19th when they suggested the holographic principle. They conjectured that probably a state of space-time within a given subregion can be reconstructed from the state of its boundary. So it's a complete one-to-one correspondence like in optical holography, when a 3D image can be encoded on 2D surface. Or we can reformulate this principle the other way around. We can say that d-dimensional theory on the surface is equivalent to d+1 dimensional theory of gravity in the bulk. And therefore, if we have this duality in some mathematical form, we can exploit it to study one system by the means of another one. And it took a few more years before Juan Maldacen realized that there is indeed a very concrete mathematical form of the duality. He has shown that a very particular form of quantum field theory, namely n=4 supersymmetric gauge theory in d dimensions, is exactly dual to quantum gravity in spacetimes with anti-de Sitter asymptotics. Anti-de Sitter is a kind of hyperbolic spacetime. You can view it as a generalization of Lobachevsky plane on higher dimensions and in real time. And a very nice feature of this duality is that it is a weak-strong duality. So originally we have two theories. Both are quite complicated, supersymmetric Young-Mills and quantum gravity. But there are two limits. On the field theory side, there is coupling constant and there is rank of the gauge group, n. And it turns out that strong coupling in the field theory corresponds to weak coupling in the gravity, and large n limit in the field theory corresponds to the limit of classical gravity on the dual side. Essentially, it means that you take your quantum field theory, which is quite complicated, at strong coupling, and you can reformulate it in terms of just classical Einstein gravity. And it is very nice because when you deal with problems in general relativity, in Einstein gravity, you just have to solve partial differential equations to describe all dynamics, all properties, and then you deal with essentially classical theory of fields in curved background to obtain observables in your strongly coupled field theory. But now, what it has to do with condensed matter physics? Of course, n=4 super Mills is a very peculiar mathematical theory which has not that many connections with real life phenomenology. But in fact, you can view your normal phenomenological field theories as deformations of this highly symmetric theory. So you take your super Mills, then you break supersymmetry, you break conformal symmetry, you can add some terms, you can consider finite charge density, and so on and so forth. And as a result, you can obtain a model. It is still a model, it's purely phenomenological. You cannot describe in holographic terms your actual real materials, but this model can be made very close to phenomenology. And the language of ADS-CFT duality still holds. So you can use the same machinery to study now this non-supersymmetric, non-conformal, more or less real-life models. So, when you think about models in terms of this ADS-CFT correspondence, it provides you a very different point of view on conventional things. So, for example, when you dualize your d-dimensional field theory to d+1 dimensional theory of gravity, then this extra dimension, and you say that your original field theory lives on the boundary and gravity lives in the bulk. So this extra dimension provides you a geometric representation of the RG flow in your theory. So like on this picture, you have different finite size excitations on the boundary, and those excitations correspond to points in the bulk spacetime at different distances from the boundary where the theory is defined. And here I have this anti-de Sitter spacetime metric. This z coordinate is parameterization for this extra dimension. So basically, it means that if you have your field theory in holographic terms, then you just for free get the full RG picture. You have your theory at all distances. You can see how different scales of excitations, of interactions interfere within your scheme. And in my opinion, it's a very nice epistemological feature of ADS-CFT. So when you want to construct some theory in holographic terms, there is a well-established holographic dictionary which connects entities in your boundary QFT and gravity in the bulk. So as I said, extra dimension in the bulk corresponds to RG flow on the boundary. If you consider not just plain ADS, but put inside it a black hole, then Hawking temperature of the black hole would correspond to temperature of your field theory on the boundary. Classical fields that you can also put in the bulk, like scalar fields, gauge fields, they correspond to quantum operators in your field theory. So for example, if you put Maxwell field in the bulk, just U1 four-dimensional field, then its scalar component, A0, would correspond to chemical potential. And derivatives of its other components, the electric field in the bulk would correspond just to electric field on the boundary. And so on and so forth. In this way, you can easily construct very different holographic models and then interpret them as some kind of field theory describing your condensed matter systems. So you can, nowadays you can include even lattice structures, you can study fermionic response, and since you can, since whatever you add to your theory still exists in the framework of classical gravity, you basically have a workaround all the standard problems in condensed matter, because you can add fermions, but your equations of motion are still classical. You don't have any like sign problem. You add chemical potential, it is fine. Equations are not getting more complicated. And since originally this duality was formulated for anti-de Sitter conformal field theory, so it was really with CFT, then it very naturally accounts for non-firm liquid behavior, because in CFT we don't have a scale, therefore our green functions do not have like well-defined poles. Instead, they have branch cuts. So while it is quite difficult to describe a conventional firm liquid in terms of ADS-CFT, if you deal with something like strange metallic phase of cuprates, then it's totally fine. And what is especially important in the context of our workshop when we speak about non-equilibrium physics is that in ADS-CFT, you can deal with real time and temperature on equal footing. And the reason for that is as follows. Normally, in field theory, you have to deal with weak rotations with analytical continuation between Euclidean and Lorentzian signatures. But in ADS-CFT, you can consider Lorentzian signature with real time. And still, it is possible to have a black hole in the bulk. So you have real time and you have temperature, and you don't need to change your language to describe both at the same time. Just to provide a very simple example of how it works, let us consider a toy model, just plain zero density conformal field theory, and try to describe how it reacts to some global quench. So what you had in the beginning, assume it is just CFT in its ground state at zero temperature, and its bulk dual is just plain empty anti-de Sitter spacetime. Now you want to quench it. How you can do it? By adding some extra entity in the bulk. So what you can do, you can inject a mass shell that will start collapsing towards the center of your ADS spacetime. And in this particular example, you get the answer for free because you know from high school that if you have an asymmetric shell, which has an empty inside, then outside of the shell, its field, like its gravity field or its electric field, looks like a field of a point-like charge. And inside, you have just undeformed empty spacetime without any fields, which means that this collapsing shell from outside looks like a black hole, and inside it looks like empty ADS. And then you can easily solve classical equations, for example, for scalar field on such a background, and then you obtain just in few lines the answer for time-dependent two-point green functions of your CFT. While doing this computation in CFT would require much more effort. But we are interested in more complicated physics. We want to study something like X-ray core spectroscopy, some Mahan-Nazier-de Vinicius physics in the regime of strong coupling. And for that, we need to add more components into our bulk holographic model. So the minimal model should include at least gravity and Maxwell gauge field, because then it would mean that you have some non-trivial chemical potential on the boundary, and you can study dynamics of charge density waves, some time-dependent response to perturbations in chemical potential. So to do that, you can consider just electrically charged black hole, which is described by this metric. And then in the static case, the T component of your gauge field would have the following form near the boundary. So its asymptotic value would equal to chemical potential, and the slope of the field would be equal to charge density. Then you perturb it in time, you see how it evolves, you solve your classical equations of motion, and you get whatever you need. Now, when we deal with models of that kind, we can consider different levels of complication. Because, yeah, the minimum setting you need is just charged black hole and some small perturbation of U1 gauge field in the bulk. But then you can consider back reaction from your gauge field perturbation onto the gravity. So now, instead of just static charged black hole, you'll get some dynamical black hole perturbed by the electric field. And that would correspond to energy transfer in your boundary system. In order to make closer contact with real systems, you can add some extra terms to your bulk action. So for example, you can add some source which will generate lattice in your boundary theory. In terms of gravity, it would correspond to some periodic modulation of your space-time, of your black hole horizon, if you wish. You can add some disorder. Also, you may ask, what will be harmonic response function in this model by adding this Dirac term to your gravity action. So in principle, you have a lot of freedom in playing around and constructing models of different levels of complexity. So I think I already said how you should proceed technically, but let me just sum it up. You don't start with some generic equations. You always, because your equations are highly nonlinear, they have a lot of components and they have a nearly infinite number of possible solutions. So you need to start with some static numerical solution of GR equations. And now there are plenty of them known in the literature. So for example, you start with some solution which simulates square lattice and finite density fermionic matter. Then you perform some time-dependent perturbation of chemical potential, or in bulk terms, of the Yuan gauge field. And then you solve your dynamical equations, which have the following form. So here R mu is a curvature, Ricci tensor, lambda is cosmological constant, which you need to get not an asymptotically flat, but rather anti-de Sitter space-time. T mu crystal and T mu disorder are just some arbitrary matter that you throw in order to get a source for your crystal and disorder structure on the boundary. So the last equation is the Dirac equation, which you normally solve in the probe limit. So you don't consider backreaction of your external fermionic probe onto your bulk setting, but rather compute its green functions in the probe limit. Then you solve all these classical equations of motion, and you obtain correlation functions by analyzing near the boundary asymptotics of your classical fields. So this procedure is very straightforward, but it's not very easy. So just for example, it's a very typical system of equations that you get when you deal with some time-dependent setting in ADS50. So here different letters correspond just to different components of your bulk tensors, some parts of your metric tensor, some part is your gauge field, and so forth. So in order to do such an analysis, you really have to be an expert in PDE. But on the other hand, they look scary, but still straightforward. So you don't have any, you don't encounter any problems that you cannot resolve, like sign problem or divergence of your perturbation theory. So if you really want to push this forward within our initiative, I'd suggest to do it in the following few steps, because definitely it would be quite complicated to consider the problem of local charge quench in strongly correlated non-Fermi liquid in its full completeness. So we need to go step by step. The easiest thing to analyze, in my opinion, would be to consider time-resolved RPS-like phenomena, time-dependent fermion spectral function. Because when you perform a local quench in a system, you break your translational invariance, but you retain rotation invariance around the point of quench. And in that case, it would be quite easy to solve for one particle green functions. The next step would be to study thermalization of conductivity, which is more complicated because it will break this rotational invariance. You have quench at one point, and you need to measure conductivity between two other points. So you get a more complicated system of PDE. And at the last stage, I would suggest to consider a more or less real crystal structure. So for example, we can simulate square lattices like what we have in cuprates, in holography. But to solve such a problem as full back-reaction equations of motion corresponding to charge local perturbation in holographic crystal lattice, this will require a real expert in numerical analysis of multidimensional PDEs. So if we are interested in proceeding along this line, we need to hire someone like that. So basically that's it. That's what I wanted to say.